Okay. Good morning, students. Yeah, Mike, please. Uh, Thank you. Let's see if it works. Bob. This button is blooped up. Yeah. These things get a lot of wear and tear. Okay, that's better. We're going to do some clicking. We have the clicking software running today, so make sure you have your clickers out. We'll be using them in just a second. We're going to review the brain burner from homework 13, and then we're going to push past that just a little bit and talk about potential energy states. And then we'll do some demonstrations. There will be some homework, and as I frequently do, the homework will be ready by tomorrow morning, Friday morning, maybe tonight, but definitely by tomorrow morning, and it'll take you over the weekend. SI session today, Friday, and 2 on Monday, so plenty of review. I would like to review a few comments or a few things from the news that affect everyone in this room. The first one is we must defeat TCU. There is no alternative, and therefore, go Knights. So I hope, did anybody go to the game last night? It must have been fun. Man, I bet it looked fun on TV when I saw it on the news. All right, second bit of news, and this is actually scientific, and you can make some notes about it because I'll probably talk about the Rosetta orbiter on the next exam and the final, simply because it is an orbiting spacecraft around a celestial body, and so we've talked about orbits and stuff in the past, and this is fair game. And this one's actually orbiting around a comet known as 67P by other names. This is the actual orbiter, solar panels, a bunch of cameras and lasers and radar and stuff like that for imaging. And what we're going to do is look at some of the images that were just published a couple days ago from the surface. And here's some pictures from European Space Agency, ESA, Rosetta orbiter. This is from July 25th, 2015. So this is a long distance view. Now this is a comet, so what you're looking at is the nucleus of the comet, and it's far enough from the sun that it's not blazing out and bright the way comets are, leaving a trail. It is leaving a little bit of a trail. You can see it is outgassing on the sunny side. So it's getting enough sunshine to be illuminated, but not enough to make it a big, bright comet. It's not quite near the sun for that. Here's another image. And you can see it's kind of real, unusual shape, which is normal for comets. Here's another one. Here's a picture from almost a year ago, 3/27/16. Here's a close-up. Okay, and you can see that it's got kind of a neck. It looks almost like, an apple core or something like that. All right, so there's a close-up of it. Now, I want to show you a real close-up that was published just a few days ago. All right, now, this is the before picture. I want you to look at it carefully. Now, you don't have to take notes on it. Just make a note. 67P has a cliff. This is the picture of the cliff. You can see the shadow, all right? And this is measured in, every pixel is a certain number of meters. Okay, so this is a decent picture. Something like what you would see on Earth. Now, this one's a little bit blurry because they were a little bit farther away. Now, here comes the most recent shot. Now, I want you to visually memorize this. Now, look at this. Did you notice anything? Let me go back. Visually memorize this one. Let's go back to the other one. Notice anything? This is the before. And here's the after. Now the shadows are a little different. It's a little different part of its orbit. Before. So that long shadow on the left, the lower left of the image, is a little bit longer in this one. Slightly different angle. What do you notice? Look carefully. What do you see? What does the observer see? Before, after. What do you see? There's a chunk gone. The cliff collapsed. See this bright area right here? Look at that. Let me go back. This bright area. This is before. Here's after. It's missing. This comet is eventually going to collapse. And you know what we get after a comet is completely gone? We get meteor showers, because all that debris and stuff, it doesn't like suddenly evaporate into nothingness. It's still there. It's just not, in one big. So the next time that goes past the sun, around the sun, actually, it might crash into the sun eventually. Sometimes that happens too. Or it might crash into Jupiter. That also happens. Jupiter eats a lot of comets. The sun eats a ton of them too. So this one, but if it doesn't, it's going to eventually, collapse. And why does that happen? Well, on Earth it happens because of sun, wind, rain, ice, erosion. Now you don't have any weather on Comet 67P, but you do have heating and cooling. Q equals mc delta T. That fractures and pulverizes any solidity, or it can, and then when that happens, it becomes unstable, just like it does here on Earth. Now, we don't have any mountains here in Florida, but if we went a little bit further north, up to North Carolina or northern Georgia, there would be mountains up there that have rocky outcroppings that from year to year change slightly due to freezing and melting water. Matter of fact, I was just looking at some pictures of a mountain in Georgia just last night, covered with snow. So they're getting snow up there, just last week. And this bright area, they think is ice. Freshly exposed ice. So if you want to read some more about that, just type in ESA, Rosetta, and 67P, and you'll be able to read a ton of stuff about that. Okay, so just a little science news. And that's by way of advertising, an advertisement for Astronomy 2002. Hey, are you guys registering for fall yet? Anybody registered yet? One person? Okay, couple. If you have to register, if you need another science class, Astronomy 2002. I don't teach it that often. Sometimes I do. But they have a bunch of really smart planetary scientists. They can tell you all about the comets, the planets, everything, the asteroid belt. All right. But now for us, let's take a look at homework 13, the brain burner. Okay, the chunk of jade hanging in a vertical spring. And your objective was to figure out the spring constant K. All right, now make a note of it here. We're going to go over this, and I want you to take careful notes because we're going to do a clicker question. We're going to go through a sample calculation from the homework, and then you're going to do it again on clicker to see how well you do. So take notes, get your calculator out, get your clicker out, and let's get going. Now, the whole idea was that you're given a chunk of jade of differing masses, and for everybody, the change in the stretch of the spring is a downward elongation. So delta y is negative 0.10 meters for everybody. All right, that was actually in the drawing, the sketch. All right, so everybody had that. And the key to understanding how to tackle this problem is the following. The fact that the jade stabilizes at minus 10 centimeters, negative 0.10 meters. And that means that since it is stabilized, the force is balanced. Okay, so there's the key. Go ahead and underline those two words, stabilizes and balance. Because if it stabilizes, that means no acceleration. Good. No acceleration means net force is zero. Good. So if there are forces acting on them, whatever they are, they have to balance. Now, in this particular one, Vanessa, there are two constituent forces. There's good old weight force, and there's some upward pull force from the spring. So make a note of that. Right now, we're going to sketch this out. And so put a dot right here to symbolize the center of mass of the rock. Okay, I'll get the rock out of the way. Right, so there's my center of mass. First force, first constituent force, good old weight force. Downward, mg, so whatever the mass is. And everybody had a different mass on each attempt. By the way, I set it so that you could have an extra fifth attempt on the homework. A couple students were asking me about that. I don't know if you guys got to try it, but you did have an extra attempt. And everybody had different weights, different masses each time. Anyways, go ahead and write a downward arrow. Now, the second constituent force is the spring force, and I'm using symbol capital F for that one. Now, for us, that's going to be negative k delta y. It's always k times a negative sign times some distance, some displacement, whether it's vertical y or horizontal x or anything like that. Okay? Now, make sure that those two arrows are the same size because they balance. The net force is zero. So if you have 10 newtons downward from the weight force, that automatically tells you that the spring, if it's stabilized, the spring's pulling up with that many newtons. Okay? And so let's work out the specs. All right, so one of the randomly assigned mass numbers is 2.1. Right? So everybody, many of you had 2.1 kilograms for one of your attempts. Okay, once you have that, you can calculate the weight force. Okay, and we've done that about 6 million times. W equals mg, and I'm using negative 9.8 meters per second squared because I want to be very careful about the up and the down directions of my forces and my displacements. Okay, my displacement is downward, my weight force is downward. And if you calculate it out, in this case, it's negative 20.58 newtons. All right, so what that means is, no matter what else you know, the upward spring force is positive 20.58 newtons, upward, all right? Because they have to balance. Now, if this thing was going boing, 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 up and down, up and down, up and down, you couldn't say that. But if it's you ease it down until it just steadies at 10 centimeters lower, then you can make this calculation. All right. Now, at this point, we're ready to use the force, the formula for the spring force. F equals minus kx. Let's bring that out now. Okay. So here it is, and it's not kx; it's k times delta y, because it's vertical. Okay, along the y-axis. Now, I know my force number, that's positive 20.58. I know my displacement, delta y, that's negative 0.10 meters. All right? Now, if you look up the spring constant on the internet, you'll see newtons per millimeter sometimes. You'll see pounds of force per inch, pounds of force, per millimeter, I suppose maybe that would be a mixture. but we're going to do newtons per meter. So we're just about ready to do that. The negative signs cancel both on the right side here. If you do bring them across the negative 0.10, it would cancel left and right. Anyways, K is positive. And there was a discussion post about this. All right, so there's your quotient. Now you just calculate it out. Okay, and this one's actually kind of easy because the denominator here is 0.10. Divide by 1/10 is the same as multiply by 10 over 1. So you just have to move the decimal place 1 point over. And there's your spring constant. K equals 205.8 newtons per meter. So that's the number of newtons for this spring that you've got to pull with in order to stretch it by 1 meter. Right? That's what the spring constant tells you. And if we were doing it in pounds of force per inch of stretch, we'd have a slightly different number, but it would be, you could do it. And if you buy a spring on the internet, they'll have both numbers, metric and English, posted. Yeah, that's better on that row. It's good. All right, so there's your spring constant. Now, we're going to work with this for just a minute. I want to point out a couple things about the spring constant. It's actually kind of an interesting number because if you multiply it by square meters, think about it, newtons per meter times, like some number of square meters will be Newton meters, all right? And Newton meters are joules, all right? Now, the reason that that's important for us, and you can make a note of this, SPE, spring potential energy, is equal to 1/2 kx squared, and we're going to calculate that next. You're going to have a clicker question in just a few minutes, so make sure you get this next calculation as well. Spring potential energy states. All right. So let's try this spring. K equals 2,000, just to have a nice round number. 2,000 newtons per meter. And let's say that we stretch it out to the right according to this diagram. Go ahead and sketch it in. 0.22 meters. That's 22 centimeters. All right, so those are fairly nice numbers. Okay. And what we're going to do is use the formula for spring potential energy to figure out the potential energy state of the spring mass oscillator at this particular position. So write down SPE equals question mark right below x equals 0.22 meters. All right, that's what we're going to try to calculate. So let's get to that. Now everything you have in this blurb up on top is in the diagram, so I'll just move the diagram up. Okay, we're going to calculate SPE. Here we go. Here it is. It's all laid out. Go ahead and take notes on it. 1/2 kx squared. Good. And so the second line of my calculation block is 0.5. And then my spring constant, 2,000. 2,000 newtons per meter. And then my next term on the second line on the right is 0.22 meters quantity squared. All right. Now, in the third line of my calculation block, I've combined 0.5 and 2,000 newtons per meter to get just a little simplified. I'm just kind of like taking baby steps here, just itty-bitty steps to make sure nobody gets caught napping. So the first two terms in the second line become 1,000 newtons per meter in the third line of the calculation block. And then my 0.22 meters quantity squared is equal to 0.0484 square meters inside parentheses. Okay, make sure you're clear about that. Do not get tripped up. And now you can see Newton meters are almost there. You see them? We got 1,000 newtons per meter in the first term, third line. And then the second term, we got a bunch of square meters, 0.0484. And so you can do some cancelization. So go ahead and cancel the meters from the denominator of the first parenthesis, 1,000 newtons per meter, cancel the meter in the denominator there. And then cancel 1 power from meters squared. So now you just got meters to the first. And usually you don't write down meters to the first, you just write meters. So I'll just cancel out the number 2, right? And so now you just multiply 1,000 times 0.0484, that's 48.4, good. That's easy. And then newtons times meters, all right? And again, let me just remind you that a newton meter is the same as a joule. And you could now go ahead and calculate this in calories if you wanted to. You know, we're not going to do that, but it's an energy. This is also 48.4 kilogram meter squared per second squared, all right? And so you can see, as I said a few minutes ago, that multiplying a spring constant times the square of a distance gives you energy. And that's the spring potential energy, SPE. Now we're going to do some more calculations. Get your clicker ready. Go ahead and turn it on. And this is going to be a calculation question. And go ahead and start. Period. We're on frequency B. Here's your question. All right. A vertical spring dips by delta y equals negative 0.15. Okay, 15 centimeters dip. Last time it was 10 centimeters dip. And you've got a 1 kilogram block of jade or whatever, you know, steel. Go ahead and calculate the spring constant. And give me your answer to the nearest 0.1 newtons per meter of spring constant. All right. And remember, when you're doing this, hit the send key or we won't get your answer. And can you turn the lights on? And we'll give you a minute or two to calculate that. We have 5 answers. Good. All right, here they come. It's good. I see a guy up here in the front row, clicker in his right hand, calculator in his left, laptop on the desktop. Good. Good. Glad to see you guys working. Good. Brianna, you doing okay over there? Good. Uh-oh. I see somebody with a negative sign. Not supposed to be any minus signs for the spring constant. Remember, they cancel. All right. 1 minute. Ashley, got it. What about it? 30 seconds. What was that? That sounded like a wolf out in the wilderness or something. Was that you guys? Gosh. All right. Uh-oh, we're over time. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, good. Most of you got it right. Here's the calculation. 76% of you got it good. All right, that's good. I'm happy about that. So the weight force, mg, is 9.8 newtons. Okay, that's on the left. And it would the weight force would be negative. The spring force would be positive. Okay, so positive 9.8 newtons on the left. A minus k, and then a dip of negative 0.15 meters. And then the minus signs cancel. And here's the cancellation. All right, so you can cancel them at this stage here. When you have a negative of a, that's like saying negative of a negative. Okay, and so you calculate it out. Now, go ahead and write that down, 65.3. We're going to use that on the next clicker question. All right? And now what we're going to do is stretch the spring horizontally, and this is going to be a calculation question. Here we go. You stretch it out horizontally now on a tabletop. There's the sketch. And you bloop it out to the right by 40 centimeters, 0.40 meters. Calculate the spring potential energy at this position. All right, so again, give me to the nearest 0.1 joules of energy. And we'll go over this calculation in case you get it incorrect. And then we have some more calculator questions after that, or some more clicker questions. Okay, so if you answer 65.3, that is incorrect. That's the spring constant from the previous question. Can you turn the lights all the way on? All right, good. So your displacement is delta x equals 0.40 meters. Yeah, so this one is calculating an energy, just like we did a few minutes ago. I am glad it's Thursday. Is that pathetic? We just had two weeks off, and already I'm ready for another vacation.
Same though, I'm so tired.
Oh, gosh. And I just drank a Monster. It's not helping. Tell you. Darian, look at this. Okay, you know how to, when you grade this, look carefully at all the answers. On these numeric ones, I think you can check all the different answers and mark them correct if they.
I think so.
Yeah, be merciful when you grade this one. Both of them, actually. But it looks like we're getting plenty of.
Yeah.
One minute. What? You what? "15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Ching. And you guys did pretty good. The answer, here it is, in case most of you got it right, 84% of you got it right. 1/2 kx squared. So 0.5 times 65.3. And that gives you 32.65 newtons per meter. That's my intermediate step, combining those two usually. And then 0.40 meters quantity squared is 0.16 meters square meters. And then you multiply it out and you get joules and a value of 5.224. So your answer is actually, to type in there is 5.2. All right, so make sure you write a note of it. At x equals 0.40, spring potential energy is 5.2 joules. All right, because now I have another clicker question for you. Hit the refresh key, because this one's a multiple choice. What?
What? Oh, sorry.
I saw you smiling. You gabbing with... All right. All right. If the spring mass has 5.2 joules of SPE, all the way out there at 0.40 meters, what's it got at the center? 0.00. Read carefully and think. Always read carefully, Stefan. And then that gives you time to think. What is Dr. B asking? "30 seconds. "20 seconds. "10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Very good. Most of you got that one right. Hey, if x is equal to 0, 1/2 of k, any k times 0 squared, ding, is equal to 0. Let me ask you this. Dun, 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 dun. What's the kinetic energy at 0.00? Go ahead and start the question. Dun, 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 dun. Dr. B strikes again. Yes! Yes! I knew it. I knew nothing that I was talking about was going to cause you to smile like that. Always something.
That, yes. That's for sure.
Always something.
That's for sure.
30 seconds. Get ready to display these results. "20 seconds. "10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Yeah. A little bit of disagreement. That means you're still, you're forming your thoughts, stuff. So let's take a look. Let's go ahead back. Let's think about this. All right. Out there at x equals 0.40, you pull it out that far, and then you let it go. Now, when you pull it out that far, you're holding it. How much kinetic energy do you have? Goose egg, 0, because you're holding on to it. Then you let it go, and it goes back towards equilibrium. As it moves to equilibrium, it's going to different smaller values of x. So the potential energy is getting smaller and smaller. All right? So once you get to 0.20 meters, you've lost a bunch of potential energy. But you've gained kinetic because you're moving. Make a note of this, my wonderful students. Maximum kinetic energy in an oscillating system occurs at x equals 0. Minimum potential energy occurs at x equals 0. So x equals 0, equilibrium, 0 potential, max kinetic. And that's if you're going left or if you're going right. When you're going through the equilibrium point, if you're in motion, you're either going left or you're going right. Okay? That's all right. You can at least say that you have max kinetic. You might have some leftward velocity. You may have some rightward velocity. But whatever you do, you have a bunch of kinetic energy. And students, make a second side note. You can figure out the partition of potential and kinetic energy at any position, as long as you know the potential energy at the start, or the position where you started. Right now, we're actually going to use that in just a few minutes. So here's the answer to this. We're going to actually study an oscillating system and the potential energy and the kinetic energy of it with some of the demonstrations up here. So what we're going to do now is we're going to do some pendulum and wave demonstrations. And what I'd like to do is turn the lights up, please. And I'd like to get 4 volunteers to come up, or 4 people up here in the front row that have timers. Do you want a time? Do you have a timer on your? Do you get? Don't look at them. Do you want a time? Do you know how to use a stopwatch? Yes? No? Yes? Okay. Do you want us? Okay, so we got 4 timers, and what we're going to do is, let me pause the podcast here, and we're actually going to go to the doc. Where's my cursor? Here we go.